All right, so now we're just going to state the limits of some sequences. You don't have to justify these with a lot of statements. Just you can just mentally say if the numerator is bounded and the denominator expands without bound, then that limit is going to be 0. If you really want to write a justification, the numerator is bounded and the denominator increases without bound. All right, that's how you would justify that, but you probably don't have to. You can just think about this sequence. You're gonna have one. You can have 1, 1/4, 1/9, 1/16, 1/25. It's going to 0. All right, what happens to this one? I'm going to have -3, -6, -9, -12. This is just increasing negative without bound, so that limit is -infinity. By the way, just if you haven't done this yet, pause the video and predict the rest of these limits. I should have had you do that in the first place. Anyway, here we go. Hopefully you've gone and predicted these after pausing the video. This one, look, it's just like horizontal asymptote. The degree of the numerator equals the degree of the denominator, so ratio of the coefficients is going to be 3/2. So essentially, you can think of this as being a function, and everything you know about the limits of functions, you can apply to the limit of sequence. Basically, you create a function that has the same values for natural numbers, and then the function, the sequence, are going to have the same limit. Okay, what if it's 1 to the n? Well, I'm going to have 1, 1, 1, 1, 1, 1. It's the constant sequence 1, 1, 1. All right, so that limit is 1. This one's interesting. So if I have -1 to the n, so what are the sequence values? The sequence values go -1, 1, -1, 1. All right, does this have a limit or not? Okay, answer, no. Look at a graph of it, and we'll see, even though I'm not requiring you to learn the epsilon definition, it's really helpful to understand why this sequence does not have a limit. Because if we try to say that this sequence has a limit, whether we try to say it's 0, we try to say it's 1, or we try to say it's -1, whatever we want, just say epsilon equals 1/2. And then for epsilon, or, I've put 1/4 here. It doesn't matter, really. For epsilon equals 1/4, clearly, no matter how big of an n I pick, I'm going to have sequence values that jump out of the epsilon band. All right? So for epsilon, really for any epsilon less than 2, all right, there is no m such that n greater than m implies absolute value a sub n minus l is less than epsilon. Because no matter how far we go out here, we're always going to have points jumping out. So this criterion can never be met, no matter what the m is, for any epsilon that's less than 2, less than the distance between these two things. All right. Did I want to say more about that? Oh, yeah. And remember about the definition, okay, because why epsilon equals 2? For the limit to exist, the criterion has to work for any epsilon greater than 0. So if you can find even one epsilon for which the criterion fails, then the whole limit fails. All right. So that's sort of going back to the epsilon definition of the limit, why this has no limit. This limit does not exist. So, in ways similar to what we have been thinking about with our limits of functions, sometimes you have a limit that's positive or -infinity. That's not the same as the limit not existing. This limit does exist, it's -infinity. This limit does not exist. It's not positive infinity, it's not -infinity, it's nothing. All right, this limit, all right, 1/4 to the n. Let's look at what those values are. We're going to have 1/4, and then 1/4 squared, which is 1/16, and 1/4 cubed, which is 1/64, and then 1/4 to the 4th power, which is 1/256, etc. So obviously that limit is 0. And that's really all we have to say about that. Now, what about this one? 5/4 to the n. So, all right, so you might notice that I'm comparing 5 sequences of similar form, and there's a reason for that. What happens to something to the nth power? What happens to 1 to the nth power? The limit is 1. What happens to -1 to the nth power? The limit does not exist. What happens to 1/4 to the nth power? The limit is 0. What happens to 5/4 to the nth power? Well, I'm going to have 5/4 for my first term, then 25/16, then 125/64, right, because that's 5 cubed over 4 cubed, and then 625 over 256. All right, what's happening to these numbers? They're getting larger. These numbers are increasing. So this limit is infinity. All right? Okay. Now, the limit as n approaches infinity is what that says, of negative 1/2 to the n. What is negative 1/2 to the n? By the way, all these are geometric sequences, aren't they? They're all geometric sequences. This one's a geometric sequence with r equals 1. Sorry, I put extra dots, but it just goes 1, 1, 1. This is a geometric sequence with r equals -1. This is a geometric sequence with r equals 1/4. This is a geometric sequence with r equals 5/4. And this is a geometric sequence with r equals -1/2. So one thing we're going to get really familiar with is that geometric sequence with a negative r alternates signs. So when I do -1/2 to the 1 power, I get -1/2. -1/2 squared is +1/4. -1/2 cubed is -1/8. -1/2 to the 4th power is +1/16. Okay, so these values are alternating sign. So are they approaching a limit or not? Well, think about a graph. So if you think about a graph, so these functions are going -1/2, +1/4, -1/8, +1/16. Are these values approaching a limit? Yes, they are. They're approaching the limit 0. You know, any small epsilon that I pick, eventually all the points are going to fall within that epsilon. So that's our hand-waving justification for the fact that this limit is 0. All right, so now let's compare these things. I have 1 to the n, this geometric series. So this is a geometric series, really. So let's observe that these are all geometric. This one is with r equals 1. This one is r equals -1. This is r equals 1/4. This is r equals 5/4. And this is r equals -1/2. All right, so we can make a generalization about the limits of geometric sequences. Right? Now, really a geometric sequence is a sub 1 r to the n minus 1. But as n approaches infinity, the -1 is not going to matter. And you're going to see that the a turns out not to matter either. That is, it doesn't matter if you started from 1 or from 12 or whatever. What matters is what the r was. So what you end up with is, if the absolute value of r is less than 1, like -1/2 and 1/4, then that limit is going to be 0. If the absolute value of r is greater than 1, like 5/4, then that limit is going to be infinite. If the r is equal to 1, that means we just go 1, 1, 1, 1, 1. That limit is 1. And if the r is equal to -1, then that limit does not exist. All right? So what happens to r to the n depends on the value of r. And it's small values of r. These are going to be the ones we're really interested in when r is less than 1. The absolute value of r is less than 1. So if r is, r could be -0.9, and r could be -0.999. As long as the absolute value of r is less than 1, that sequence is going to converge to 0. And that's going to be important to us. Okay. Yeah, next let's just look at a couple problems from the book, and then we'll be done with this intro.